Spectrophotometry. In this video, we will be demonstrating the use of a spectrophotometer. Previously, we had prepared a series of solutions using the original copper amine stock solution and 4 dilutions using the serial dilution method. After a series of dilutions, the copper amine solution will be analyzed using a spectrophotometer. To do this, we are placing the solution into a cuvette, which will then go into the spectrophotometer. We are carefully dispensing the solution into the cuvette using a transfer pipette up until the mark on the cuvette. There are a total of 6 cuvettes. The first cuvette will be filled with water. It is the blank cuvette. The second will be filled with the original stock solution. The last 4 cuvettes will be filled with each of the diluted solutions. This is the blank cuvette filled with water. Here, we are loading a cuvette into the spectrophotometer. Before loading, we wipe the cuvette free of any dirt or fingerprints. We do this so that the light generated by the spectrophotometer travels clearly through the cuvette, ensuring an accurate absorbance reading. This is repeated for each cuvette loaded. We open the spectrophotometer and load the cuvette, closing the lid afterwards. We first loaded a blank cuvette filled with water and zeroed the spectrophotometer. This is important in order to provide a clean baseline for an accurate reading of absorbance and eliminate any erroneous absorbance data. We then removed the blank and loaded the cuvette filled with stock solution. For this cuvette, we will scan across all wavelengths for 2 reasons. First, we scan across all wavelengths in order to observe how the absorbance changes across every wavelength. Secondly, we scan across the wavelengths to find lambda max, or the wavelength where absorption is highest. With the peak absorption of the stock solution, we record the wavelength that corresponds with it. We then input that wavelength into the program so that the following absorbance analysis of the dilutions would be scanned on this wavelength. We then load the cuvettes with the dilution and scan each of the 4 dilutions and record the absorbance data for each dilution. Let's talk about absorbance. In this lab, we measured the absorbance of different samples of different concentrations. So what relationship does concentration have with absorbance? The Beer-Lambert law defines this relationship. The law defines that absorbance is equal to the product of the concentration of the sample times the molar extinction coefficient times the path length or wavelength of the light passing through it. The law also defines that absorbance is directly proportional to the concentration of the solution and the wavelength of the light. This is shown through our procedure and data. In the procedure, we found the wavelength of peak absorption by scanning across all wavelengths of the stock solution. We then used this wavelength for the following absorbance analysis. In our data, we found that the concentration is directly proportional to absorbance. The greater the concentration, the higher the absorbance value. This makes sense because with a greater concentration, there will be more solute particles within the solution that absorb light, increasing the absorbance value. In the graph, we see a negative linear relationship between concentration and absorbance, with the absorbance decreasing as the solution is diluted.